Okay, so this is the 2024 Higher Level Applied Maths Leaving Cert paper, question 1. So this one is fairly straightforward. I think you just have to multiply these two matrices. So we've got matrix A here and matrix B here, calculate AB. So I've done this already just to save a little bit of time. So I have A here and B here. What you need to do here is multiply the rows in A by the columns in B. So for example, if we take row number 1 here and column number 1, if we multiply those two, where they intersect is going to be here, so that's where we're going to put our answer. So I put the answer here, and we can see it's minus 1. So you multiply minus 1 by 5, 0 by 0, 2 by 2. That's what I've written here. When you do that, you get minus 1. Now you don't have to write all this out necessarily in the exam. It will take too long. I've just written this out just to show you what I'm doing. If we take, let's say, this row here, the middle row here, and the middle column here and multiply them, they intersect here at 4, right in the middle. So that's where the answer is going to be, right in the middle here. When you do that, you get 2. So we multiply 3 by minus 1, 1 by 4, minus 1 by minus 1. That's what I've written out here, and we get 2 down here. Let's just do one more. Let's say this row here and this column. Well, they will intersect here down at the bottom right. So that's where I've written out how I've done it. And the answer down here is 6 down at this bottom right corner. So let's see, what do? You multiply 0 by minus 2, 2 by 3, and minus 3 by 0. That's what I've written out here. And the answer is down here on the bottom right. And that's really it for part A. Okay, so this is part B. A security manager wishes to install cameras in the public areas of a shopping centre. She wishes to locate these cameras so as to minimize the total length of the cables between them. In the network shown below, node O represents the manager's office. The nodes A to L represent the locations where the security cameras are to be installed. The weight of each edge represents the distance in meters between each location. Using an appropriate algorithm, find the minimum spanning tree for the network. Name the algorithm you used. Relevant supporting work must be shown. Okay, so there are two ways of doing this. One is using Prim's algorithm and the other is using Kruskal's algorithm. I'm going to do it both ways just to show you that we'll get the same answer. But you can skip on through the video if you're happy enough with both of these or one of them. So let's have a look at Prim's algorithm first. So with Prim's algorithm, what you've got to do is start, let's say, at O here where the office is, and you've got to find the edge of least weight going from O. So that's going to be OB, which has a weight of 20. Then once you have that drawn, you look at all the edges from O and B and find an edge of least weight. So the second one is going to be 45. It's going to be up along this way. So then you'll have O, B, and A drawn. So you can do that on the graph if you like. Maybe I'll do that. So let's see, we've got OA anyway, or sorry, we've got OB anyway, I should say, and then we're coming up here to A. So after that then you've got OB and A. You've got to look for an edge of least weight going from OB and A. So the edge of least weight going from OB and A would be down to C, which has a weight of 56. Now we've got O, B, A, and C, so now you've got to find an edge of least weight going from those, and you can see that the edge of least weight is going to be this one along here, which is 43. So once you've got that done, now you've got to find an edge of least weight from E, C, O, B, and A. So let's see, we have 82. Now if we were to draw a line, let's say for example here from C to B, that would result in a cycle. We can't have any cycles in a spanning tree. Similarly here 62 will form a cycle here, so we can't use that one either. So the numbers that we have are 82, 62, 96, 73, 71, 89, 109. So 71 and 62 we can't use because they'll form a cycle. So the next one we're going to use is going to be this one here, 73. That comes out along this way. So now let's see, we have 96, 71, 82, 62. A lot of those are going to form cycles. We've got 89 is going to form a cycle. The next one is going to be down along here to F, from D to F, which is 27. After that then we have, let's see, 48 will come out along here. We've got a 66 along here, So I'm going to go for 48, that's the smallest one. And after that then we have 59 is going to come out along here. And then we've got, let's see, 100, we've got 88, 103, 97, 66 is going to be the smallest one without causing a cycle. And then after that we've got 100, we've got 88, so it's going to be, and we've got 102, 97 will cause a, coming down along here, that will cause a cycle, so we can't use that. We've got 103, so 88 seems to be the smallest one, so we're going to come up along here. And then let's see, we have 21, that's going to be the smallest one out along here. And after that we've got 40 up to K. Let's see, do we have anything else? We've got 102, 100, 97 will cause a cycle, 103 will cause a cycle. Everything else is going to cause a cycle, so it's going to be up along here to K. And that would be it for Prim's algorithm. Now what you could do, it says show relevant work down here. What you could do is maybe put in the edges as you go along, so you would maybe the edge and the weight here as you go along. So the first one we did was AB, so you would put, or sorry, OB I should say, you could put in OB and 20 and so on. I won't write all of them in, but you could maybe do something like that. And that's your minimum spanning tree. Let me see, what else do we have to do? Name the algorithm, we've done that. Relevance porting work would be maybe this table down along here. Okay, so let's have a look at Kruskal's algorithm then. It's the same kind of thing, but this time we're going to list all the edges and the weights in order. So I've done that already to save a little bit of time. Prim's algorithm is probably going to be a little bit quicker, I think. With Kruskal's, as I say, you've got to draw this table here, all the edges with all their weights, and they're all in order from lowest to highest. So what you've got to do then is draw the minimum spanning tree. So we're going to start with OB. So OB is here to here. That was at the very beginning. O and B were here, and that has a weight of 20. So I'll just tick that off as we go along. IL was the next one. That was way over here on the right. So I'm going to draw that in here. This is IL, and that had a weight of 21. DF was the next one. Now that was in the middle here. So D was here, F was here, and that has a weight of 27. The next one was KL. So KL is actually out here at the end. K was here, and that has a weight of 40. The next one was CE. So that was actually down here. This was C, and E is here, and that has a weight of 43. And AB then is 45. So A was actually up here. That comes down here to B, and that has a weight of 45. FG is the next one. So F to G, G is down here somewhere, and that has a weight of 48. And the next one is OC, and that has a weight of 56. GJ, so from G to J, J is actually out here. That's going to come along here, and that has a weight of 59. OA is the next one. Now the problem with OA is if we were to draw from O to A here, we end up with a cycle, so we can't use that one. So I'm going to put an X next to that one. DH is the next one. Well, D is here, and H is actually out here somewhere. That has a weight of 66. The next one is BE, which is 71. So from B to E again, that's going to form a cycle. If we were to come down here, we're going to end up with a cycle here. So we can't use that one. The next one is AD, so we can draw that one, I think. Yeah, AD is over here, and that has a weight of 73. The next one is BC, which is 82. BC will actually form a cycle here, so we can't use that one. The next one is IJ. So from I to J we can draw, so I'll draw that one, and that has a weight of 88. The next one, just tick that off. Next one is ED, I'll tick that one off as well. Well, actually, let's have a look at it first. ED from E to D, that's actually going to form a cycle, so I'm not going to use that one. End up with a cycle here. So ED, I'll put an X next to that one. BD is 96. So let's see, from B to D, that's going to form a cycle, so I can't use that one. The next one then is FH. Can I use FH? I think I may actually be finished at this stage. Yeah, FH is going to form a cycle as well. Yeah, in fact, all of these will be cycles, so I can't use any of those remaining ones. I've ended up with the same spanning tree as I did earlier when I did Prim's algorithm. Okay, so let's have a look at the next part of this question. It says, calculate the shortest total distance the security manager would have to walk if she starts at her office O and follows the minimum spanning tree to visit each of the camera locations in the shopping centre. Okay, so what she's going to have to do, I'll look at this one here. She's going to start at O. So what she's going to have to do first is come down here, go over to E, and then come back again. So we've got to do 56 plus 43 twice. Once she's back here, then we've got to go to 20 over to B, then 45 up to A, then 73 out to D. Now she's got to go out to H, which is 66, and then she's got to come back, which is another 66. So we've got to do 66 twice. We've got to go down 27, 48, 59, 88, 21, and up to 40. Now where does she end up? Does it say? Calculate the shortest total distance security manager would have to walk if she started at her office and followed the minimum spanning tree to visit each of the camera locations in the shopping centre. No, so she can finish at K. So you've got to go down here and back again, across here, over here, back again, and then down along here and then up to K. So you've got to add all those up. So it's going to be 56 plus 43, which you've got to multiply by 2. She goes out and back. Then she goes out to B, which is 20. Then she goes up to A, which is 45. Then she goes out to D, which is 73. Then she goes out to H, which is 66. And she comes back again. Then she goes down to F, which is 27. Then she goes down to G, which is 48. And then she goes over to J, which is 59, then up to I, which is 88. I'll just come down here. Then she goes down to L, which is 21, and then up to K, which is 40. When you do all of that, you get 751, and that's in meters. So that's it for part B. John is cycling on a straight horizontal road at a constant velocity of 10 meters per second and is 21 meters behind another cyclist, Kevin, who is cycling at a constant velocity of 4 meters per second in the same direction. John begins to accelerate at 2 meters per second squared. 1 second later, Kevin begins to accelerate at 4 meters per second squared. Calculate the times when John and Kevin overtake each other. Okay, so let's just have a look at what's actually happening here. You have, first of all, you've got John. Let's say John is here, and out here we have Kevin. And we know initially that they are 21 meters apart. John is currently cycling at 10 meters per second and is 21 meters behind Kevin, who is cycling at a constant velocity of 4 meters per second in the same direction. John begins to accelerate. So John is going to accelerate here, and he's going to accelerate at 2 meters per second squared. Kevin is not going to be accelerating initially. He's going to continue on at the same speed for 1 second. John is going to start at 10 meters per second and accelerate at 2 meters per second squared. So what I'm going to do first of all is just have a look at what happens in that first second. What's going to happen is John, first of all, is going to travel a distance of s is equal to ut plus half at squared. So his initial velocity is 10. His time is 1 second. Plus a half. He's accelerating at 2 meters per second, and it's going to be 1 squared, t squared. So when you work that out, you get 10 plus a half of 2, which is 1. 1 times 1 is 1. So he's going to travel a distance of 11 meters in that 1 second. Now what about Kevin then? How far does he actually go? If you look at Kevin then, he goes a distance of, his initial speed is u, which is 4, t, which is 1, plus a half. Acceleration, he's not accelerating, so that's just all going to be 0. So he is going to travel a distance of 4 meters. So if we have a look at that, just in that 1 second, John travels 11 meters, Kevin travels 4 meters, that means that John has gained 7 meters on Kevin. So in other words, we can draw a new diagram after that second. So we can start with John, go out to Kevin again. So this is John, this is Kevin, and we now know that the distance between them now will be 7 meters less. So in other words, the new distance between them after 1 second is going to be 14 meters. It's just 21 minus 7. Let's start from there then. We now know that John is accelerating at 2 meters per second squared still. Kevin has started to accelerate now at 4 meters per second squared, and his initial velocity at that time is 4 meters per second. John, on the other hand, we've got to work out his initial velocity. So if you take, let's say v is equal to u plus at, his initial velocity was 10 meters per second. He accelerated at 2 meters per second squared over 1 second. So that brings him up to 12 meters per second. So his initial velocity, we'll call it u at this stage. It's v over here, but it's u once we finish this second, if you like. Once we start the next period of time, his u is going to be 12 meters per second. So now we've got to work out from this phase when overtaking will take place. So we want the two distances to be the same, in other words. So if we take John's distance travelled, it's going to be s equal to ut plus half at squared. So his initial velocity is 12. The time we want to work out of overtaking, it's going to be half his acceleration, which is 2, and it's t squared here. We want that to be equal to Kevin's distance, which is 4 times t, ut, plus a half his acceleration, which is 4, and it's t squared here as well. But the thing about it is John has to travel an extra 14 meters. So in other words, Kevin will travel 14 meters less. So the distance that John has to travel is going to be this distance here plus another 14 meters. So all you've got to do is solve this for t. We'll end up with a quadratic trinomial here, which we've got to solve. So let's see, we have 12t plus t squared is equal to 4t plus 2t squared plus 14. Let's just bring everything over to the right hand side here. 2t squared minus t squared is t squared. 4t minus 12t is minus 8t, and then we've got plus 14 here. So let's just solve this. We're going to have to solve this using the quadratic formula. So t is going to be equal to minus b, so it's 8 plus or minus the square root of b squared minus 8 squared minus 4 times 1 times 14, all divided by twice 1. If we do this, we get t is equal to 8 plus or minus, let's see, we've got 64 anyway, and then we've got a minus 56 divided by 2. So this will give us a t equal to, you've got to do the plus and the minus version, and I've just done this to 2 decimal places, but I've gotten 5.41 seconds, and I've also got 2.59 seconds. So these are our 2 times after the first second, so what we've got to do now is just add a second to each in order to get the overall time for overtaking. So my answers are t is equal to 6.41 seconds and t is equal to 3.59 seconds. And that's it for question 1.